All right, you guys. So the past couple days, we were talking about arithmetic sequences. We talked about how to be able to find explicit and recursive formulas for those sequences. Well, now we're moving on to geometric sequences. A couple of you guys kind of got confused as far as when was something arithmetic. Remember, arithmetic is whenever it's going up by the same term. For instance, 2, 4, 6, 8 is going up by a positive 2 every time. You could have also had 1.5, 2, 2.5, 3, 3.5, where it was going up by 0.5 each time. Or you could have even had it what we called going down or going up by a negative, where it was something like 8, 5, 2, and -1. So we would call that going up by -3. And remember, in that case, we talked about a common difference. With geometric sequences, very similar process, still going to be identifying the first term. However, now we're going to be talking about a common ratio instead of a common difference. So this question is asking us to identify whether or not the following sequences are geometric, and if so, create an explicit and recursive formula that represents the sequence. Give you a quick hint, they are both geometric sequences. And the reason why is because both of them will have a common ratio. So this first one, 6, 18, 54, and 162, we're multiplying times 3 every time we go up. 6 times 3 is 18, 18 times 3 is 54, 54 times 3 is 162. So we're multiplying each time. Now we talked about how to be able to find that common ratio. Since we're multiplying to go to the next term, we could find the common ratio by using division. So I'm just going to give you a little side work up here on top. If we did 18 divided by 6, we should get that common ratio of 3, and then continue. 54 divided by the 18, common ratio of 3, and then 162 divided by the 54. Once again, we're getting that common ratio. So we're dividing the fourth term by the third term by the second term by the first. So you're dividing a term by its previous term to see what our ratio is. And so in this case, we've already identified that our common ratio, or what we denote as R, is 3. And then also we need to know our first term. Our first term is just the first term of the sequence, which is 6. So I'm going to go ahead and do the same thing over here since we've already identified that they are both geometric. This one's a little more confusing because we see this oscillation of positive numbers and negative numbers. I think a lot of times people forget that if we multiply by a negative, it's going to give you the opposite result of what you started with. So in this case, I'm going to go ahead and do what we did up here to find those common ratios. I'm going to do that as some side work. So 4 divided by -2 gives me -2. -8 divided by a +4 gives me -2. And then +16 divided by a -8 gives me -2. So we can see over here, our common ratio is -2, and our first term is also -2. Now, don't get these mixed up. I think a lot of people, when this happens, think that this -2 is simply coming from here. That's not true. This common ratio is coming from the division that we did over here. This -2 is our first term. It's coming from our sequence. It's coming from this -2 being the first term. So now let's go ahead and go back over to our first sequence, and we're going to write out our two formulas. So we need explicit formula and recursive formula, both of which only need the common ratio and the first term. So the explicit formula is a formula that we're going to use to eventually to be able to find terms that are way far away from that first term. So in this case, we can write the explicit formula as a sub n is going to be equal to the first term times the common ratio raised to the n-1 power. And so in that case, we can go ahead and plug in the things that we know, our first term and our common ratio. So a sub n equals, our first term was 6 times our common ratio is 3, and we have that n-1 power. And we're finished for the explicit formula. Not too hard, right? Let's go ahead and move on to our recursive formula. Recursive, it's going to be very similar to the recursive formula we dealt with when we had linear sequences. You'll have a sub n equals r times a sub n minus 1. So notice with the recursive formula, this is a subscript. This n minus 1 is a subscript, and then with the explicit formula, it's actually the n minus 1 is represented by an exponent. That's where we get that idea of exponential recursion. So in this case, when we do this, I like to read it in math speak as the term that we're looking for is going to be equal to the common ratio times the term, the previous term, which is this n minus 1. So we're not going to plug anything in actually for the a sub n or the a sub n minus 1. All we need to do is plug in our common ratio. So a sub n is going to be equal to 3 times a sub n minus 1. Remember with a recursive formula, you also want to identify the a sub 1, our first term. And so I'm going to go ahead and write that down here, even though we already have it up here. I'm just going to rewrite it so you can see the complete recursive formula. And we're finished. So you can see being able to identify the common ratio and the first term are paramount to being able to finish an explicit formula and a recursive formula. And really, after you know those two things, it should be pretty simple. So in this case, on this side, I'm going to go ahead and do the explicit formula over here. So your explicit formula still follows the same formula. A sub n equals a sub 1 times your common ratio raised to the n minus 1 power. In this case, when we're plugging in our first term, our a sub 1 is negative 2. Our common ratio is also negative 2. And we're going to leave it as to the n minus 1. So no simplification like we had to do, or no distribution or anything like we had to do when we had linear sequences, arithmetic sequences. With geometric, we plug them in, we're finished. And then we can also do the recursive formula. So remember the recursive formula, it's going to be a sub n equals r times a sub n minus 1. Remember that is a subscript, not that we're plugging something into that at this point. We know our first term. I'm going to go ahead and write that. First term is going to be equal to negative 2. Put this little semicolon to denote a separation, and then we'll write out our formula. A sub n is going to be equal to the negative 2 that we get from our common ratio times a sub n minus 1. And we're finished with the recursive formula. So some other things that we've talked about are how to be able to convert back and forth. Similar to how we did arithmetic sequences, as long as you know this common ratio and this first term, really you should be able to do both. So if I'm dealing with an explicit formula and I have something like this, automatically I know my first term, I know my common ratio, I should be able to put my first term and my common ratio in the recursive formula, and vice versa. If I had the recursive formula, I automatically know my first term, which goes there, and I automatically know my common ratio, which goes there. So this one should be pretty simple going back and forth. In order to use them, we're just going to be plugging into our explicit formula. To be able to find the 10th term, we'd plug in 10, 100th term, we plug in 100. Don't forget with these, we're going to get really big numbers, so don't freak out when that happens. So we're going to go ahead and continue on from this, talk about some application problems today. And by the end, we'll be able to mix the two, the arithmetic sequences and the geometric sequences.